In these next two slides, we will use the phase diagram of water to review some basic definitions related to phases and phase transitions. Most small molecule substances exist in three phases, specifically solid, liquid, and vapor. Anticipating the conclusions of Chapter 3, where we will use the second law of thermo to learn about the stability of these phases, we find that the solid phase exists predominantly at low temperatures over a range of pressures, while the vapor phase exists predominantly at higher temperatures. The liquid phase is found at intermediate temperatures. These three regions of the phase diagram are best represented on plots of pressure, the y-axis, versus temperature, the x-axis. These regions are separated from each other by curves where two phases exist in equilibrium with each other. We will call these curves coexistence curve. So there is a solid-liquid coexistence curve, a liquid-vapor coexistence curve, and a solid-vapor coexistence curve. Coexistence curves intersect at a specific pressure and temperature called the triple point, where the solid, liquid, and vapor phases of a substance are in equilibrium. We often discuss phase diagrams by describing the phases that are observed when we heat up a substance from very low temperature to high temperature under a constant pressure. If we consider the case of the substance water at standard pressure, that is at 1 bar, we see that water exists as solid ice below the temperature of 0 degrees Celsius, as liquid water between the temperature of 0 and 100 degrees Celsius, and as water vapor at higher temperatures. When the solid-liquid coexistence curve is crossed, the solid crystalline ice melts into liquid water. This is the melting or fusion process. As the liquid to vapor coexistence curve is crossed, the liquid vaporizes. This is the vaporization process. Going in the opposite direction by decreasing the temperature under a constant pressure of 1 bar, water vapor transforms into water liquid at 100 degrees Celsius by a process called condensation, and water liquid transforms to water solid at 0 degrees Celsius by a process called crystallization, since a crystal phase forms from the liquid phase. In general chemistry, you may have been taught that the latter process is called freezing. I would prefer that you use the word crystallization over freezing, because crystallization does imply the formation of a crystal phase from the liquid phase. On the other hand, freezing also applies to the formation of glasses by cooling of liquids. A glass is a non-ordered solid substance, which has significantly different properties from crystals. Some substances find it difficult to achieve molecular order during cooling, and end up forming glasses as the temperature is lowered from the liquid state. A glass is not a true thermodynamic phase because its properties change with time. So to avoid confusion, we should talk about crystallization rather than freezing when we want to refer to the liquid to crystal transformation. The subsequent transformation of solid to liquid and liquid to vapor upon heating is observed at any pressure above the triple point pressure. We will now consider what happens when we are heating a solid substance, let's say ice, under a constant pressure that is lower than the pressure of the critical point. We see on the phase diagram that solid ice transforms to water vapor at a temperature T, denoted T sub, for sublimation. The direct transformation of this crystalline solid phase to vapor phase is called the sublimation process. The reverse process, when the vapor phase transforms into the crystal phase, is called the vapor deposition process. It is important to remember that sublimation and vapor deposition processes can only occur at pressures below the triple point pressure.